denote S the maximum complexity that I can get here. So what I want to show at the end of the argument is to say that S is large enough. That is, formally S is maximum over all axes of length n over this conditional complexity.
No, it's a bit strange because
what?
If we know what it is,
No,
it's a bit indirect. So we first define this maximal thing, and then
I take this threshold and I show that it cannot be too small. Just from some counting argument.
Yeah, so you imagine that all this is less than this, and get a contradiction.
Yeah.
So you can even avoid mentioning S explicitly, but why not?
Okay. So I say that now I will introduce a strange definition. I say that P is how suitable or what? How they define it?
Suitable.
Suitable. Okay. P is suitable.
P is what?
P is a program. P is suitable for x of length m.
Yeah.
If first U maps P and nothing to x, that is, P behaves like a program for x.
Yeah.
And second, complexity of P given x is small enough. That is, there exists a program Q of length less than not greater than s, such that complexity such that Qx is P. So the idea is this P looks similar to a to the shortest program, which maps x. P looks similar to the shortest program for x. In particular, if I take
so you say that P is simple.
P is simple conditional to x.
The program, not the complexity.
Program or length of P?
That's strange.
Length of P, yes. Length of P, yes. Yes,
But why don't you write it in a shorter way than the complexity of what?
It's more or less equivalent. The complexity of.
Yeah.
Okay, I can write it in an equivalent way. That is, P is suitable.
Yeah.
If two complexity of P given x is not greater than s, and first U maps P.
The complexity of P given
or length of P again.
The complexity of the length of P given is.
The length of P.
So
and we fix here
But this is
a parameter S, right?
Yes, S is a fixed parameter.
just wait a bit. So the program.
If I take the real shortest program for x, then this real shortest program for x, yes, then it is suitable for x.
And why? It depends on that.
Oh, assuming that x is a maximal.
Yes, yeah. Because s is the maximum.
And X is
S is
the
the
string
maximum.
for which the maximum is attained.
Yeah, if I take any x of length m,
for any.
for any x, its shortest program is suitable. But maybe there are many different suitable programs.
it does not matter whether you write P or length or P.
Here?
Yeah, I think.
No, it's very important.
Okay, yeah, it's important. Yeah. Okay. Yeah.
Or not.
So the shortest program of every string is suitable.
Actually, if we know if we know the length, then we can what you mean? If we know the length,
then
we can reconstruct a program just waiting.
Maybe not exactly
but
this one, but
some other. There can be many programs. So it's
formally it's not the same yet.
Up to some difference in that.
Yeah.
So.
And now the main.
So we want to get a contradiction, assuming that S is small.
Yes, assuming that S is small.
So we assume that S is small, and then for every X we have a suitable program.
Or several suitable programs. But at least one.
Yeah, but also we can, for example, we can take X for P, and it's always suitable. Or trivial program which is suitable because it has length just
it can
simple.
But the length is typically
no.
We can say.
So the point is that not only shortest programs are suitable,
but trivial
also
programs,
other ones.
Trivial programs are also suitable because their complexity.
But I think the main idea should be that there are more suitable programs than just the shortest one. And the property that P is suitable is enumerable given X. The property that P is the shortest one is not enumerable, right? I think that's the main idea.
Yes, say it again.
The set of pairs S, X, P, such that P is suitable.
X.
Triples.
Yes. Such that X is suitable for P.
Yeah. It
is enumerable.
Yes.
And the set of tuples X and P, that P is the shortest problem for X, is not.
Yes.
That's the idea.
Yeah.
Why he needs that notion of suitable.
Okay, so for suitable program, we definitely have some suitable programs.
Yes.
But so now, what is the plan?
The plan is to show that for some X there are lots of suitable programs. For some X, there are more or less 2 to the n, in fact 2 to the n over m suitable programs.
And where we use that S is small? Here.
And here we get the contradiction with the assumption that S is small. If for one single X there are a huge number of different suitable programs,
then there exists one with high complexity.
Yeah. No, then you need P here, not the length of P. If you want to get contradiction.
Yes, you're right. Yes, that's important.
So here is P2, yeah?
Yes.
So now we have lost the property that the shortest program is suitable.
But some shortest program is still suitable.
Yeah. There might be no shortest program that are suitable.
No. Because if we know the length, we can reconstruct one of them. So length has small complexity.
I agree if you say that here we, in the definition of suitable, we write S minus constant. Or S plus constant. Where S is defined in this line.
Okay, yes, S minus constant. So the S is here, this.
Okay, so it becomes more and more strange. So can you just okay say something more and maybe become clear.
So we want to show that for some x there are many suitable programs.
Yeah.
Following Gash, I denote by mi is the set of x such that there exist at least I different suitable p. Maybe more, but at least I. So M0 is in M1, is in M2. No. The wrong direction. M0 is the greatest. Here is some M.
And in fact, M0
J?
is equal to M1.
No. Oh yeah, in fact it is equal. And the last one is empty, and this one is not empty.
Okay, but can you explain why we consider what is the plan? Why we need all this strange things? So, what is the idea? How?
We want to find an x which has many suitable programs. So we want to find non-empty M with very large G.
Okay, it is just simple formulation.
Yeah, absolutely.
Okay, but why?
Just, I want to show that this chain is long enough. Just a reformulation. Yeah, if this mj is not enough, is not empty, then it contains some x, and we're done. But look, we know the size of this set, M0.
It's all the...
Yeah, it's 2 to the n.
Yeah.
And I want to show that for two neighbor sets in this chain, the difference of sizes is not very large. And if the difference of sizes is not very large, then the chain must be long.
So we need the chain to be 2 to the n over n.
Yeah.
So
I want to show that the size of mi plus 1 over mi is greater than something. It's not too small.
And at what is this something?
Technically, I will write logarithms. Log of the next is greater than log of mi minus what? Minus several log n.
So it's some power of.
So it's down, I don't know, n to the.
So the logarithm decreases by the logarithm of cardinality of mi can decrease only by order log n, right?
Yeah.
There is some the mi plus 1 is smaller. Yeah.
Yeah.
So you should write something.
Then we will obtain the bound like n
over log n, yes.
Or order log n.
Yeah.
But it's enough.
Yeah, and here we get, so the maximal j is of order n over some constant of log n.
Okay, and what then? I think everybody already has understood what shall we do then.
Yes, then we get an x which has at least n over log n suitable programs. So s should be greater than log of this thing.
Why?
Because all suitable programs, all suitable p are of complexity not greater than s, conditional to this x. because of this.
Ah,
Just,
and there are too many of them.
but it's somehow rather strange.
Yeah. So there are
One of strange things is that we define as like complexity of some length, and then we use that complexity of program, not its length, is
No, but
greater than S.
we have discussed.
yeah, it was as prime.
We discussed that this is not really much different because if there is a program, if it's the shortest program, then knowing the length we can.
We can reconstruct one of these programs.
So now we have a very special, isolated question. We want to show that the difference of sizes cannot be too large.
So you say that if for many x there are some suitable programs.
If for many x there are I suitable programs, then for some reasonable fraction of them, there are in fact at least I plus 1 suitable programs.
And what's this?
And 1 over n divided by 4.
Yeah, 1 over n. The idea is the following. In fact, I can find a point x and mi plus 1 minus mi such that complexity of x
What is very strange? You measure the number of suitable program with completely unrealistic precision up to 1, and then
I don't say that there are exactly I plus 1 program, at least I plus 1.
okay, yeah, but the difference is that you just want to
Okay, so I can explain what is the profit of the difference. Assume we have some x, and we know for sure that it is in mi plus. No, in the other direction. In the other direction, of course. It is in mi, but not in mi plus 1.
Yeah. So we have some mi. Each of them has some I or more shortest program.
Exactly I.
Exactly I.
Exactly I. And that is very interesting, because it is in the difference.
No, in the difference we have exactly I. And here we have I, at least I plus 1.
Yeah, but look at this.
But wait, in the definition of mi, we have 2 to the I or just I?
No, just I. What is
Just
very strange. The precision is unbelievably exact.
And look at this point which is in the difference.
Yeah.
You can enumerate all suitable p for it, right? That you know the number, the I, and you can find them all by brute force search. And after that, you can, you know its complexity, exactly.
It's
Complexity of this x. You know all. You know the list of all potential shortest program for it, and you can get the real shortest program for it.
So you say that the list of all suitable programs
It contains
determines complexity.
Yes.
But wait, I don't understand anything at the moment. So we have fixed I, right? And we consider a string for which the number of suitable x's is exactly I.
Yes.
Right?
Yes.
And then, given I, we can enumerate, find all these suitable programs.
Yeah.
Yes.
And
the shortest of them will have complexity. Will be the shortest one because we know that the shortest
among them
one is
there is the
suitable.
shortest one. Okay. And
I don't know.
And you know that its complexity. So for this x, you can calculate its complexity.
As the length of that program.
Yeah.
But we don't know which one is the shortest one. I don't understand.
Now, if we have a list, if we know I,
Yeah.
we can generate the list of all suitable programs.
Okay.
Take the shortest one, and therefore we know the complexity of x.
No, the shortest one is just suitable. It might be not the shortest program.
No, shortest program is always suitable. This is our...
No, the other way around. Why every suitable? It's part of definition that suitable programs are programs.
Yes.
I see. So, okay. So given I, we can find the complexity of any string in the difference in between mi and mi plus 1, right?
Yeah.
And where is the contradiction?
No, there is still no contradiction.
Okay.
Okay.
But we need to know the whole set here exactly.
Yeah. So if you know, if by some miracle you know the whole list of mi plus 1, then you know you can enumerate the difference, and for each point in the difference you know its complexity.
Okay.
Okay.
So again, given I and luck, some luck, that we know mi plus.
But we can measure this luck. The luck is more or less a log of mi plus 1. Just you need to know the number of strings in mi plus 1 to enumerate.
Yeah.
So if you want to enumerate this ring, this difference, you need to know the number of points in m plus 1 plus some additional information to know the numbers, the number s, the number I, the number n, which is now some logarithmic additional information. So with this information, you enumerate this ring, and if you need for some reason a string of high complexity, you enumerate it. For each point you calculate its complexity and see is it large enough or not. If it is not large enough, you continue your search. So just the idea is that if you know in advance that in this difference there exists a point of high complexity, you can find it.
Okay.
So on one hand, complexity of this point will be high. In fact,
It should be log mi.
Yeah, it should be more or less log mi.
Since there are many strings there.
And on the other hand, it should not be greater than this, the number of points in mi, log of the number of points in mi plus 1 plus some small additional information. And if you compare one thing and another thing, you see that the difference between logs of mi and mi plus 1 is very small. Otherwise, it would be a contradiction.
So how the difference affects the whole bound between the upper bound and the lower bound between complexity?
I take the point of maximal complexity in the difference between mi and mi plus 1. On one hand, its complexity is close to log mi. On the other hand, it is not greater than log m plus y, log mi plus 1, plus some small additional information.
And so we want to conclude that log m plus y, mi plus 1, therefore should be close to log of mi.
Yeah.
Otherwise we get a contradiction because the maximal complexity is small.
Yeah.
And so...
and this argument, there was one very small cheating, probably you can see it.
There is general cheating.
Okay, at the very end there was some small evident cheating. I take the point of the indifference and claim that its complexity should be close to log mi, or at least not less. In fact, it's not always the case.
So you mean that the complexity difference minus the...
If the difference is very small, it could happen that there is no...
but if the difference is very small, there is nothing to prove. No, this is not cheating. Cheating in general structure of the proof.
But you look, it's very short.
Gach is extremely clever, but he should be... Okay. But can you explain to me what is happening here somehow? So I understand. I can tell you what I understand, and maybe you can, starting from this point, you can explain what you do. So why the complexity? Let's consider whether the complexity of x when x is, why it cannot be very small. So imagine the case when it's extremely small. Imagine there is some function which computes kphi of x given x. Then we get a contradiction in a standard way. We look at all the x's and find one which has high complexity. Since